All right, today we're going to talk about area. So, what we need for area is, much like with distance, you have rulers. For areas, you have a reference region. Generally, this is a square. And here I've drawn a square with sort of unit length sides 1. Say 1 inch, 1 feet, 1 something. But let's just say let's just say that this was supposed to be 1 feet on each side. All right. So the fundamental unit is this square. This is how we compare things. So let me try to okay, so what I've done here is I've duplicated that square. So this thing is now we've got 3 feet on the bottom here and 2 feet on the top. And essentially the idea is how many 1 by 1 squares do we have inside. And so to compute that, you can kind of like shift and just kind of fill in this thing. You can see that that top row, you've got 3 squares, right? And that's because, there's 3 feet going along. And then you can do the same thing for the bottom, but let me just draw it in here. And okay, and so now you can see you got 6 squares. Now where's that 6 coming from? Another way to compute it without having to actually physically draw these squares. Well, that's 2 times 3, right? So here we've got the height of this thing being 2 feet and the width being 3 feet. And so the area is 2 times 3, or 6 square feet. That was 2 times 3 equals 6 square feet. So that says square feet. And what that means is it's literally 6 squares whose sides are 1 feet by 1 feet. So we don't know what the area of a 1 by 1 square foot thing is. We are just using that as our reference point. It is what it is, right? And we measure everything related to that. We can have another unit, 1 by 1 inches, and if you draw that out, well, there's 1 inch there's 12 inches in a foot. And so just like we did here, if we wanted to do that, you can mark off 12 little marks there and 12 marks going up, and it would be 12 by 12 equals 144 square inches in 1 foot. Okay, and then that means that each of those little squares, 144 square inches, would go into each of these boxes here, and so 6 square feet is the same as 144 times 6 square inches. And 144 times 6 is 864 square inches. So that's how the units work, right? So converting from feet to inches linearly, like the 3 feet would be 3 times 12, 36 inches. But for areas, you've got the 2 dimensions that you're converting both into. And so it becomes, you multiply both those linear conversion factors. So 12 by 12, 144 square inches per 1 square foot. All right, so that's that. Now, where is this area thing coming from in terms of the relationship of reality and math, right? So in reality, you could have, an actual 1 by 1, 1 foot by 1 foot square tile, and you can actually, you draw a rectangle out and you can measure that out, right? And what is the mathematical assumption that's going on there is that as you move that figure around, right, the area of that figure is not changing. That's what we're assuming. And basically, if you put, 2 rectangles, a rectangle and a copy of itself right next to each other, then you double the width if it's left-right placement. If you go, so for example, these 2 things, that's twice the area of the original square. And if you do these 2, then you again twice the area. So doubling the height doubles the area, doubling the width doubles the area. And if you double the height and the width, you get this, which is you quadruple the area, right? Because you got the 2 going left to right, and then you're doubling that height, so you get those extra 2. So double, quadruple. Okay, so that's squares and rectangles. Rectangles are pretty simple in the sense that all you do is whatever their dimensions, if it's I don't know, 1/2 foot and 3 feet, then you multiply them together, you get 3/2 square feet. And notice how when you multiply these things, because that one dimension was 1/2, when you multiply it by the other thing, you're ending up with a smaller number, right? So 3/2 square feet, the 3/2 seems smaller than 3. I mean, it is, but it's now a different unit, right? And so that's, comparing them in that way is sort of odd, right? It's just, what the 3/2 square feet means is you can fit 1 1/2 1 by 1 squares inside. And so, but you can't do it nicely. You can't actually put a single square foot tile in there. You have to break it up. And, basically it's, that's just the way it is. Okay. Okay. So, let's now do a little area-based problem solving. So we have a square here. Let's say that what we want to know is the length here. And let's say that I say, and it's a square, so the width and height are the same. And we know that the area is 36, and we want to know what the side lengths are. So the area is x times x, which is just x squared. So squaring is just multiplying by itself. The name is inspired by this exact problem, which is if you make a square out of that length, squaring the length is what the area is. Anyway, so we have x squared, and by assumption of it being 36, the area, we know that x squared equals 36. So the question is, what is x? How do we figure that out? So 36 is in fact the square of a whole number, so this makes it pretty easy. 1 times 1, or 1 squared, is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. So I'm just going through them. 5 squared is 25. 6 squared is 36. And 7 squared is 49. So 6 squared being 36, that's our answer. X equals 6. So that's pretty easy. All it required was knowing the squares of these integers, and the area that we're interested in was that. Now, if you look at the numbers here, 1, 4, 9, 16, 25, 36, 49, you'll notice a lot of numbers in between are missing, right? You should also notice that squaring a number is an increasing thing, meaning like 3 squared is larger than 2 squared, right? That's generally true. If you square a larger number, you get a larger number for the area. Okay, good. Now, what happens if a number is not easily, is not the square of an integer? There is a number whose square it will be, but we need a little bit more work to figure it out. So let me erase some of this stuff. And now let's do another. Let's say the area is 40. So what would be the square root of 40? So we want x squared equal to 40. Well, if you look at the numbers we have here, 36 is less than 40, and that was 6 squared, and 49 is greater than 40, and that was 7 squared. So just from that, it's basically somewhere between x is between 6 and 7. Okay, good. Now, typically, one would simply use a calculator to do this. There's a little magic function called the square root of 40. That's how we write it. Square root of 40. And why do we call it that? Well, it's the root of the square, right? So it's the side length of the square whose area is 40. So this little function is exactly solving our problem. That's just the math way of saying it. And if I was wearing my math hat, mathematician hat I should say, saying the square root of 40 is exactly the only thing I can really do here. There's a few manipulations I could do here, but basically the square root of 40 is not a number, is not a whole number, which I can't write down. It's not a rational number, which isn't clear, but so I can't write down a fraction or a decimal with a repeating pattern. It is really kind of a new and different kind of number with numbers that just keep repeating. So I can't write it down precisely in like a decimal form. I can only write approximately. So it's all about approximations. Now, on our calculator, here's our calculator. We have 40, and you can do two things. One is 40 raised to the 1/2 power, or 0.5 power, and that's that. So our calculator is saying that 6.3245 keeps on going. So that's one option on here. And this is this calculator is a app called Graphing Calc 83. It's on the iPhone, and it simulates the TI 8384 interface, which is a standard calculator to use in math class. Some people like it in real life, but I find that the app is quite nice if you can get it. I don't know what's on Android, but anyway, so you can see this radical symbol. That's what the squiggle thing is, a radical. And yeah, so 6.3245555, whatever. So maybe actually rounds up to 6, I guess. 5 and up is 6. Let's just say 6. Anyway, okay. So that's the calculator, and you can consider it done at this point. But I don't consider it done because it's just this magical, mystery thing that you type into this calculator, and it's like, what? How do I get that? Why does that make sense? So, how would I do it if I didn't just hit the magic calculator button? Well, this is what I do. Let me get rid of all that. All right, so I know it's between 6 and 7, but what do we have? We've got 36, and we've got 40, and then we've got 49, right? So that's a step size of 4 between 36 and 40, and that's a step size of 9 between 40 and 49. So, if you think of 4 as a single step, then 9 is 2 steps, more or less, right? And so 40 is 1 step away from 36, 2 steps from 49. So it's 1/3 away from 36. So it's basically 6 plus 1/3. Or, now 1/3 is like 0.333. I'm just going to go with 6.3. This is all very rough. It's wrong. This is not correct. It's just kind of correct. All right. And what am I actually suggesting here? Well, get to that in a moment, but let's test it out. 6.3. So here's my guess. I get 6.3 squared. So 6.3 squared. And of course you can actually multiply it out, right? 6.3 times 6.3. You can do this quickly. There's 4 digits in this thing. 2 decimal places, so you should have that. Anyway, so remember to do left to right arithmetic. 6 times 6 is 36, so you get a 3 here, and then you have a 6, and 6 times 3, 18. So 6 and 1 is 7, and then you have the 8, and then the next level is shifted over by 1. 3 times 6 is 18, so that's a 1. Then you've got an 8. 3 times 3 is 9, so that's a 0, an 8, 9. And now we do our adding. 3, 8. We got a 6, carry that. 16, carry the 1. And then a 9, so 39.69, right? Just simple multiplication. Really quick to do in any event. 39.69, so that's pretty close. And but that's not quite 40, so we should also do 6.4 squared, right? And 6.4 times 6.4. Again, you can just do this all out. You get the 36. 6 times 4 is 24, so that's an 8 and a 4. Next level, 2. Let's see, 24, so that's a 4. 4 times 4 is 16, so that's a 5. And then we get a 6. We get 3, 0, underscore. That's a good sign because we wanted it to be over. We wanted to get to 40, so with the number in between, and we get the 6, and so this is 40.96. And verify that on the calculator. Times that. There we go. All right. So now we're at 40.96 and 39.69. Okay. Good. So we're doing some ugly computations here, right? All right. So now I need to figure out my next number. So it's going to be between 6.3 and 6.4, right? And we had 39.69. Let's just say 39.7 and 40.96, which is 40 0.96, so let's just say 41. So that's about 1.3 in between. And the 40 here, that's 0.3, and over here that's kind of like a 1. And so maybe something like, so this is thinking of it as step size of 0.3. 3 times that is kind of 0.9, so that's the next one. So it's 1 step for 3 steps, or 1/4. So we do 1/4 of the distance between 6.3 and 6.4, or try 6.325. Okay. Again, you could do this with multiplying this all out, but now it's going to get harder, and we get 40.005625. So 6.325 squared is approximately 40.006. So that's pretty good. So that's pretty good for what we're trying to solve for. It's already got 2 decimal places. And you could continue like this. You could figure out, so this is slightly above 40, so maybe try 6.324, square that out. You can kind of find out the difference there, and that's how you can keep going. You just keep trying to make a guess in between these 2 numbers, and eventually you'll get as far as you like. There are other methods for computing the square root in a more precise fashion. Perhaps we'll talk about it. But ideally, this is sort of what I want to convey here is This doesn't work just for squaring, it works for a lot of things. You try a value, you get a guess, you try another value, you get another guess, and then you look for something in between, and you try to kind of feel your way in between. So if something is closer to the one guess than the other, then your next guess should be closer to the guess that was closer, right? That's the kind of reasoning. Get things done quickly, even if you don't understand the algebra or whatever. There's a lot of problems where nobody could solve it exactly. Anyway, this method works pretty well a lot of the times if you can get close enough to the solution to start with. Notice in the way we got to 6 and 7 was because we kind of were computing these things out and we got nearby. Okay. Okay. So next problem will be a rectangle problem. So we have a rectangle like this. We don't know the side length here, x, and we don't know the other side length either, but we know that it's 3 more than the other side. And let's just say that the area here is, let's go with 72. See what that number does for us. So 72. So area is width times height. So x times x plus 3, which is equal to 72. Now, there's an algebraic way of solving this, which is basically, let me just do another color here, say orange. If I put in this orange dotted line, that to be 3 and x there, then this is sort of x squared here and 3x here. So those are the areas. So basically x squared plus 3x equals 72. So we distributed the x to here, and that's what you get. And then you do x plus 3x, subtract 72 from both sides to get it into the standard form, x squared plus 3x minus 72 equals 0. And then you use quadratic formula, which I haven't told you about. That'll be next week, hopefully. But the idea is just a kind of a plug and chug formula. It's almost like the square root function. It's like this magic thing you throw in there, except we can derive it. But so that's kind of the algebraic way. We're not doing that today. All right, cleaning it up again. All right, so how do we do this? Well, we do it by guessing, right? So let's just play with some numbers. So this is just guessing. X equals 5 leads to the other side being 8. And 5 times 8 is 40. All right, so that's too low. Let's try the next one. Let's try 7. And that leads to 10. So that's nice and easy. 7 times 10 is 70. Ooh, that's pretty close. Let's do one more. So x is 8. Leads to 11 for the other side. And then, so that's 8 times 11, which is 88. Okay, and that's too much, as I would expect. So we can do something similar as before. We kind of have 7, and we had 70 here. We've got 8 and 88 over here. And now, what's 72? 72 is over here. So that's kind of a difference of 2. That's kind of a difference of 16. So that's 8 times. So if this was a step size of 1, this 2 here, then 6. So it's sort of like 1 to 8, right? So sort of 1/9, which is reasonably close to 1/10. So the next guess I would suggest would be 7.1. And that leads to 10.1. And when we multiply these out, and of course this is going to get a little bit messier, but we can do it. 5 digits in total in the answer, because there's 3 and 2 here. And we get, with a possible leading 0, 7, and then that's a 0, 0, 0, 7. I believe that's how that would go. And then the 1, 0, 1, looks like 0, 1. All right. So that's 7171, 71.71. So that's cool. And now, so that's already pretty close. 7.1 is pretty close, and it's going to be presumably between 7.1 and 7.2. So I could just do that real quick. Okay, well, top line is the same. And then the second one would just be double the one before. So 7272 dot. All right, so we've got 7.1 is at 7.171, and 7.2 being at 72.72, and we want 72. So that looks like basically we had a 0.3 here and a 0.7 here, more or less. Or yeah, I shouldn't use the kind of a, well, what would that be? That would be one of them. Yeah, so that'd be 0.3 and 0.7 for that. So 3/10, kind of an extra step between 0.1 and 0.2. Now 3/10 of that difference between 0.1 and 0.2 is 0.03. So then we would try 7.13 as our next guess, which of course leads to 10.13. And yeah, so you could again do that multiplication, and since you've already done some of it, it's not too bad. But in the interests of time and my sanity, I'll just do that out. So that's 72.23 basically. So that's too much. So 7.12 times 10.12. Oh, interesting. 72.05. So 7.11 times 10.11. Okay, so it's again going to be somewhere between these two, which was the 7.12 and 7.11. looks like it would be close to 7.12 and so forth. So let me demonstrate in GeoGebra how this might work. All right, so I've got the input bar. I'm going to create a new variable. Let's say it's S. And I'll just go with S being 7. All right, and I'm going to construct a rectangle. So 0, 0 is our starting point. The height is 0s, right? So that's that one thing. And we need to change the view here a little. Okay. And now the length, the width, say, is s plus 3, right? Oops. S plus 3. The width was going horizontal, so we put that in the x-coordinate. And we get there. And now we just create that fourth point there. And that's our rectangle. Once we select all the vertices. And you can see that it's 70 is the area on the side, but let me show the label. There we go. So that's 70. We want it 72. And so S being equal to 7.1, you can see how that works to 71.71. And we're going to want to, here we go, have more decimal places. Let's just go for the max. All right. Okay, so that was 77.1, and we have 1, and then 2, 4, 6, 8, 7. Okay, 77.117 is pretty close. And what was it? So I would say 7.1165. Ooh, that's nice. Let's try 6. 7. Ooh. Anyway, so we can go on like that, and then just sort of to give you what the solution ought to look like. If we go back to this, oh, sorry, I already erased it. Go back to the quadratic. It was x squared plus 3x minus 72. And so this is what a quadratic looks like. I just typed in that stuff on the left, and in GeoGebra, to get that solution, intersection with the x-axis, and there you go. 7.1168439698070043. So if you do 7.1168439698 times Whoa. Okay, that was weird. 4, 3, 6, 9, and 10.1168. 4, 3, 9, 6, 9. You get something that's just so close to 72. All right, so basically those are some of the ways to solve this problem. I'm very partial to this kind of guessing method where you basically guess around until you get close, and then you try to figure out just how far, you got these two guesses, kind of the distance between them, and try to guess a bit with that. Now, there is more I could say about that, but let's turn to another matter. All right, let's move on to triangles. So, triangle. Let's do a right triangle, like so. Oops. Close enough. And let's just say we had the one side is height 2 and the other side is length 3, like so. Then what is the area of this triangle? Well, right now all we know is that the area of a rectangle is length times width. So imagine that I make a new rectangle that looks just like the other one, except it's flipped across this diagonal, this hypotenuse. So on the top is 3, on the bottom, on the right side is 2. And we have that this is a right angle, and we have that this is a right angle. And, basically, the angles here have to, well, basically, these two angles are the same. These two angles are the same. And because they're all part of a triangle with a right angle, both of them end up being right angles. So we do have a rectangle, and so 4 right angles, and so the area is 6 of the rectangle. Well, since the orange triangle and the black triangle are exactly the same kind of triangle, they're just flipped reflections of each other. They have the same area. Same area for the two triangles. And so, the area of the one triangle plus the area of the other triangle has to equal the area of the rectangle. And so, and since these are equal, we have that 2 times the area of one of these triangles is the same as the area of the rectangle, or the area of the triangle is 1/2 the area of the rectangle, right? So here, that's 1/2 of 6, which equals 3. Good. Now, in general, if you have a right triangle, same logic applies. Just say that's a right angle. Let's call the tall part here H and the small part B. Then what we have is that the area is 1/2 base times height. Okay, cool. And now we can try some other triangles. All right, so let's say that the triangle looks like this triangle, for example. Well, let's say that I call this the base, B. And now, what would the height be? Well, the height would be a line that you draw down from the opposite vertex, and that makes a right angle with the base. So that's the perpendicular. So we'll call that H. And what do we have? Well, we have, let's call this L for left and R for right. So B equals L plus R, right? And from what we just talked about, we have that the area of the left triangle is 1/2 H times L. And the area of the other triangle is 1/2 HR. So this is 1/2 HL plus R, or 1/2 HB. So it's the same formula. All you have to do is figure out what that H is, which, you can draw it in, and there's some angle stuff that we can talk about later. But so that's that kind of triangle. Now, there is a kind of another way of viewing this, which is largely the same thing, but in some sense it's ever so slightly different. If I draw on this line, I create two rectangles, a left rectangle and a right rectangle. And the left one, that's the one we care about is half that rectangle. And on the right side, the one we care about there is half that rectangle, and there we go. So it's really the same thing that I just did, except, it's kind of incorporating the previous step into it. Good. All right. Now, there is another kind of triangle that might be of interest. One where the height, so this is the angle here at this place is greater than 90 degrees, so it's kind of wide, an obtuse angle. But the formula still holds. So we've got H here. Now the base is no longer the base of this big rectangle, though. It's the base of that triangle from here to here, right? That's the base. Base times the height. The height is no longer hitting the base, it's hitting this other extended line segment from that base. So how do we view this? Well, there's a couple of ways, just like before. But one way of doing it is, again, we've got sort of two triangles. We've got this red triangle, whose area is, let's just, I'll call this L over here. So its area is 1/2 HL. And then we have another right triangle, this green one here. And that area is 1/2 H, and then it's L plus B, right? Cool. And the triangle that we care about, well, is going to be the difference, right? So this green triangle is the area of the red triangle plus the black triangle. So if we subtract out the red area here, then we're left with 1/2 HB, and that's the area of that black rectangle. So it's a very similar argument, but there you have it. All right. So let's see how we could explore this in GeoGebra. So let me put on some points here. I'll just make it a couple of free flowing points like this. All right, here's my triangle. Let me show the area. All right. And let's see. I'll have this segment AB being the base always, so we'll get that value going. So that's C. And now what I want to do is draw on a perpendicular from C to that base. Find the intersection of that. Also easy. Let me hide that line here. Okay. And let me just put in a segment because, oops, where did it come back? And let's get that value shown on the diagram. What? Okay, so now we have, oops. Oh, what? Okay. Alrighty. So, the area of this triangle is the 9.5, and we have 4.61 and 4.12. Let's see if I can, I don't know if this works. C times G. Does that give me a number? It does, 19. And so that was wrong because I forgot about the 1/2, right? There we go, approximately 9.5. Excellent. And now let me drag around one of these points. So as you can see, the height just moves along here. Oh, I've lost my height. Okay. Let's see. Maybe I need to draw in a line between these 2 points. Let's see, that would be, okay, so that's H, And let me, the intersection of, so I still want F, that was the perpendicular. Now I want to use that line H. Does that work for me? Yeah, there we go. Okay. And now, I feel like, there we go. Let's hide that line anyway. Well, I guess I should have it. Maybe I can just restyle it. Let's make it a dashed line. Yeah, there we go. Excellent. So now we have a dashed line. And so as I change the C, I'm not changing the base at all because I'm not changing B, just changing the height. And as you can see, I've got the area, this D over here, is the same as this area of the triangle. Doesn't matter how narrow, how far out, how in, how large. You can scale it out. It don't care, right? Formula is always true. Now let's see what happens if I move B. So I'm changing my base. It don't care. It's still doing the same thing, right? Probably cares. Ooh. There we go. 0 for everything. What happened there? The height is 0 because it's not a triangle anymore. So it does need to be a triangle. Well, I guess it still works. Height is 0. Yeah, formula works there too. Okay. Anyway. So that's for every triangle anywhere ever. 1/2 times base times height. All right. Now let's talk about circles. So we'll start with GeoGebra. Here's a nice circle, the unit circle, radius 1. So that means that all the points here are distance 1 from the origin here. This is the equation, x squared plus y squared equals 1. So that's nice. Now, what's the circumference? Well, circumference is 6.28. So this is 2 pi times 1, 1 being the radius. And now what's the area? Area of this thing, 3.14. This is what pi is. Let me just put on, let's see if they have pi. Yeah, pi here. Let me change the settings here so we can actually see more decimal places, because I love my decimal places. So the area, so radius 1, area is pi. So if I were to cover this with squares of size 1, you get 3.141592653 of them. All right. So what is a square of size 1? Square of size 1 is like these guys, right? So you have kind of 4 of them on the outside. And maybe I can actually just probably write this. So that's a square of size, this is a square of size, side lengths 2 from 0 to 1. And so it's at most an area of 4. And then you can get a square inside. There we go. That's our other polygon. That has area 2. And so already we have the side lengths here are the square root of 2, and so when you multiply them together you get 2. So just from the squares you can put inside the circle, you already know it's between 2 and 4. 3 is a reasonable guess, slightly over 3. You can kind of see that it, well, I don't know, it's kind of long but more shallow here, farther deep. It's a little unclear which one actually wins. But anyway, that's those areas. Now, what happens as we increase the radius? So let's go to 2. Let's zoom out a little. So now the circumference is 12.57. What happened to my... That's weird. Okay. Anyway, so this is basically 4 pi. Why? I don't know. Let's go to the next one. Let's try radius 3. What is radius 3 like? Well, here we have 6 times pi, and over here we have 9 times pi. So how is 6 related to 3? Well, it's 2 times 3. How is 9 related to 3? Well, that's 3 squared. So hypothesis at this point is the circumference is 2 times pi times r, and the radius is pi times r squared. And so it is. And you can tell that as I change it, that's exactly what we see, even on the smaller level. So the area gets a lot smaller more quickly than the circumference. And then as it gets larger, the area gets much larger more quickly than the circumference. All right, so that's the circle. Now, we can ask ourselves, how can we figure that out? Because that's the fun in life, right? So we'll just take as given that the circumference of the circle is 2 pi r. So we have a circle here, and we have r going like this, and we're saying that if you were to travel around here, that this thing would be 2 pi r. Okay, and then we're also saying that if you were to color in the circle, that area would be pi r squared. Now, how can we see that we're supposed to multiply by r? It's always a good question. Well, let's take this circle. So what do we know how to compute? We know how to compute rectangles and triangles. I like triangles. So imagine we draw a bunch of triangles like so. Imagine that I was actually good at this, and they were all the same. So we have n triangles, and all the same. Okay, and n is large, which means that I'm going to have lots and lots of triangles, and that means that the base here is almost the circumference divided by n. You have n little segments going around. Their sum will be how we measure the circumference. Basically, there's n of them. So one of these guys has just c over n. Now, what's the area of such a triangle? Well, the area is 1/2 times the base, right? So it's 1/2 base times height. Well, the base, we already said, was c over n. And what about the height? Well, these are very narrow triangles. And so, and the sides here, let me use a different color for those. All these nice blue, blue, blue. The blue ones are r, the radius. And so the height is almost the radius. Awesome. So it's 1/2 circumference divided by the n times the radius. Oh, there we go. Times the radius. So that's one triangle area. All right. So lots and lots of little these triangles. For example, if this angle here, if we wanted to do 1 degree here, that would be n equal to 360. You'd have 360 little triangles going all around the circle. And so each of the bases would be 1/360th of the circumference. Now, what is the total area of all these triangles? Well, it's almost the same as the area of the circle. So area of circle is approximately n times the area of the triangles, right? So there's n of them. You add up all their areas, and that's approximately the area of the circle. So what do we have? We have n times 1/2 c over n r. The 1/2 came from the triangles 1/2 base times height. C over n was the base, r is the height. Well, n times this thing with an n in the denominator gets canceled. We have 1/2 CR, and C was 2 pi r, so we have 2 r's. The 2's cancel, and we're left with pi r squared. So I haven't established where this pi comes from or what that is. I haven't established that the circumference is 2 pi r at all. But if you just take that as a fact, then the area follows pretty much from this argument. This is a little bit of the idea of that one sees in calculus, with sort of cutting things up into very small pieces. And I'll just mention something else. And namely, let's say that I wanted to compute the area of this figure. So how might I do this? Well, basically, one can do little rectangles like this and sum up all these little areas. And I could probably, this nearly rectangular part, have big rectangles. And then you have small rectangles where things are changing a lot. And then you just add up the areas of the rectangles, and that's your area of the big thing. This may seem kind of dumb in the sense of, that's it? Of course that's what we do. But that is what we do. In calculus, you write down some formulas for all these things, and you compute some stuff as the number of rectangles gets very, very large. But the basic idea is this. You break up your very hard problem, finding the area of some random thing like this, just like looking at it, is pretty hard. But covering up with a bunch of rectangles, that's not too hard, both practically speaking. If we actually had this thing in front of us and we had some rectangles, you could just do it. And also in terms of formulas, if you've got a formula for this region, you can figure out through the magic of integral calculus how to compute these things. So that's basically the idea of areas in all of this. All right, so we went over the basic thing of rectangles, height times width, and then we did a couple of problems where you're given the area and you want to find the dimensions. I suggested a guessing method, but that's sort of a quadratic kind of problem, so we'll hopefully see that next week. In terms of other ways of solving that problem, hopefully I presented something that makes some sense and that you can just feel like you can do, because it's just guessing. And then triangles, the area is half times the base times the height. Didn't mention how to compute the height. That's for another time. And then circles, how to relate circumference to area. And basically, if you can remember the circumference is 2 pi r, then maybe that argument I just showed would help you that, oh, okay, so because of the triangles 1/2 base times height, that's how we're going to the area thing. The height is the radius. You got all these little triangles. The base is kind of a stand-in for the circumference, and so it's 1/2 times the circumference times r, so it's pi r squared. So there you go. Until next time.